the overview once again before we actually dig into some complex actually circuit connection. Maybe I can actually give you the brief so you can recall the basic of the BJT or the transistor. So you all know. So basically, you all know about the diode, right? P-N junction. So this actually transistor here we are actually depicting a NPN transistor. So we are cascading a N-type with P-type with N-type. So that is NPN transistor. And we know, the name of this terminal, right? Emitter. Then the central region is the base region, and there is another one is called collector actually region. We know everything. So this is emitter region, this is base, and this is in the collector actually region. So based on the voltage actually applied to these three terminals, like the emitter or base or the collector, the BJT can actually, or the transistor can actually act in three different regions. Like one is called cutoff, active, and saturation. So different actually region or the mode has different purpose. So basically, the transistor can be actually used as amplifier. It can be used as actually logic devices or in memory actually devices. So in this actually course, we'll be mainly focusing on this actually regime, which is called actually active regime. So in the active mode, the transistor can be actually used as amplifier. So we'll be actually discussing about it. So what is that active region actually called? So we have emitter actually base. So that emitter base in the junction has to be in forward bias actually mode. Whereas the collector base junction should be in actually reverse bias mode. So if you wanna actually recall what is called the forward bias and reverse bias, do I need to actually explain it, or you all know it? So how do we maintain the forward bias in emitter base actually region, and the reverse bias actually condition in collector base actually region? So that is one of the case maybe we can discuss. So what we can do here, emitter is N-type, right? This is N-type. The base is P-type, and then the collector, that is N-type once again. So now, if I connect, as I mentioned, this emitter and base, that emitter and base has to be in forward bias condition. So forward bias means if we connect a DC voltage with the negative voltage here and the positive voltage here, and then connect, connect like this. So can we call it in forward bias condition? Let's say there's some positive voltage. So this voltage is positive voltage. So if I apply this voltage, you see the negative terminal of this voltage is connected to the N-type region, and the positive terminal of this actually voltage source is connected to the P-type region. So this junction or this actually region will be in forward bias condition. So that will be in forward bias condition. Whereas the collector based region should be in reverse bias condition. So what would be the case? You see, this is N-type, so it has to be opposite. So the positive terminal of a voltage source, another voltage source, we don't know, let's say we name it as V2, that is connected to N terminal of the collector region, and the negative terminal should be connected to the positive terminal of the base region. So this NP or this junction, that TN junction, would be in reverse bias actually region. So do you understand this one? So that is called the active. This is the actual condition for the active mode region for a transistor. Probably you have learned about it in probably previous semester or the previous semester. So what is the impact of this forward bias in this case? Since it is in forward bias, then current will flow from the P to N type, so in this direction, due to this forward bias actually condition, and this is reverse bias condition, so there will be no current. Means generally current should flow P to N type, but since it sorry. Sorry. Since it is in actually reverse bias condition, again, the flow of, the current should be in this direction. So the current will flow, in this direction. So that is a, a little bit of overview of, the BJT actually, or the transistor mode of operation. This is, for the NPN transistor. We can actually use the similar actually analogy for the PNP transistor. For details, you can check, I think this book. This is by actually Sadra Smith, microelectronic circuit, and I was actually looking at this condition. So I will later on actually share, both, the slides as well as, the book in the Google Classroom for your actually reference. So this is the structure of, NPN transistor. Probably we all know about it. Just to, refresh your mind, this is actually a symbol for, NPN transistor. So how do you know this is NPN transistor? So since this wrong. Give me a second. Yeah. So basically, this is the NPN transistor. So we can actually identify, NPN transistor by looking at, the arrow sign, right? So this is called N, this is called P, and this is called N. So P to N, this arrow sign would be in the emitter side. So that's why this is called emitter. This is called base, in the base, where we'll apply, the voltage in most of the cases. And this is called, collector. So this is nothing but the symbol. This is nothing but the symbol. Same applies for, PNP transistor. So this is P, this is N, and this is P. Remember, we actually put, this arrow sign from P to N. So P to N. So that's why we put an arrow sign here. Since arrow sign goes to, emitter side, so this one should be emitter for our case. This one should be in the collector, and this one should be in the base. Now, in order to actually bias this actually transistor, NPN or PNP transistor, we know the condition. We know, the base emitter should be in, forward bias, whereas, the collector base should be in reverse bias. So I think I have actually discussed it, in the previous case. You see, the base and emitter should be in forward bias, since this is P, this is N, and this is N. So this is NPN transistor. So since this is P, it has to be connected to the positive terminal of the biasing voltage, and this is N. So negative terminal should be connected to, the negative terminal of, this junction. So base emitter junction is in forward bias, whereas this collector base, the collector base should be in actually reverse bias, as we mentioned it earlier. So you see, this is the positive terminal of this actually voltage. We denoted it by, VCB, just it's a name. So it means, this voltage is being applied between actually collector and base. So this positive terminal is connected to the negative N type, side, and this negative terminal is connected to the P type actually side. So basically, this is in reverse bias actually condition. Same logic applies for, the PNP transistor. So this is basically PNP transistor. You can actually check it at home. So for any actually question or any confusion about, this basic, the symbol and, the biasing of the biasing of, transistor in the active mode. Any question, so far? Up to this, any question? Are you listening to me? Means,
sir, can you repeat the biasing part again, please?
Okay, sure. So is there any actually internet issue, means the connection issue? Is it disrupted or, something interrupted?
No, sir. No.
So if there is some interruption, let me know. Sometimes internet connection doesn't work properly. So for the biasing, am I clear that in order to run this actually transistor, no matter it's PNP or NPN transistor in active mode, because this is the most actually important mode for transistor, because we can use it as amplifier, we can use it as memory devices or logic devices. Later on we'll discuss about the amplification part or other actual part. So for that case, we need to make sure this transistor is in active mode so that the emitter based region should be in forward bias, whereas the collector based region should be in reverse bias. So how do we ensure the forward bias and reverse bias? Maybe I can give you another hint so that you will understand. What is wrong with this? So for time being, just forget about the transistor and other things. Do you recall the diode? Do you recall diode? This is diode. So diode, it has two type, right? P and N type region. So can you tell me, if I want to actually operate this diode in forward bias, what should I do?
Have to give positive voltage to the P side and negative to the N side.
So is it clear? Like this is the positive
Yes, sir.
terminal of the voltage source. We can put any value to voltage source as long as that is greater than the threshold voltage for silicon. This is 0.7 volt, means it has to be greater than 0.7 volt. Then this diode will conduct, right? So we know this is in forward bias condition. So similarly, what is the condition for the reverse bias situation? What do I need to do here? Opposite, right? There's a positive terminal should be, this is again P type segment, this is N type segment, and this is the positive terminal and the negative terminal. So negative terminal should be connected to the P type actually region, and positive terminal should be connected to the N type region, so that this diode will be in reverse bias, so there will be no current flow in this case. Do you understand this part? Like this forward biasing of diode and the reverse biasing of the diode. So basically, when we talk about the PNP junction or NPN junctions, NPN transistor in our case. So basically, it's nothing but two diodes. This N and P, that will actually make a diode, and this P and N region will actually create another diode, just like this. So as I mentioned, we are just naming this region as emitter, this one as base, and this one as collector. And as I mentioned earlier, in order to make sure this actually transistor is operating in active mode, this emitter base junction has to be connected in such a way it will maintain a forward bias condition. So how do we actually ensure this is in forward bias condition? The N type should be connected to the negative terminal of the voltage source, and the P type should be connected to the positive terminal of the voltage source. Is it clear now?
Yes, sir.
So same applies for that other region, means the collector based region, but make sure this one would be in reverse bias condition. So exactly same thing is occurring here. I just you see this voltage source, instead of actually using the conceptual like schematic, we replace it with a like symbol. This is the symbol for the transistor, right? Probably you learned it in the previous semester or previous semester, as you mentioned, in the first class. So it's just refreshing the memory. So now, is it clear? Otherwise, we'll actually discuss it many times while solving the problem, mathematical problem or something. Is it fine? Then I will go back to the lecture slide. So this is the lecture slide. I got it from the chairperson, because he is taking this class in another actually section. So he advised me to actually follow this lecture notes. So I'm actually following the similar actually lecture note, but I will try my best to make it as easier as possible. If you don't understand any part, feel free to ask me anytime. So So far we discussed about the biasing and other things. So there were some configuration, like since it has, like the transistor has three terminals, the collector, emitter, and base. So we have multiple options to choose, like how we connect the input and how we actually obtain the output. Depending on that, there might be some permutation or combination. So there will be multiple actually configuration for the transistor. So one of the widely used actually configuration is called common emitter configuration, or C configuration, it says. So what do we actually understand by common emitter in the configuration? So first, before that, generally we use the NPN transistor. Do you have any issue with labeling this one as the NPN transistor? Yes, this is NPN transistor. Is there any confusion? No, right? Because this is a symbol. This is a symbol. So since there is an arrow sign here, so that point actually that node denotes actually the emitter. This is the emitter actually region. This is the actually base region is written here, and the top one is the collector region. So that is the symbol, but as the name suggests, it has to be common emitter. What does it mean? That the emitter should be common between input and output. Means emitter should be a certain node which is common to input and output. How is it possible? The easiest way, when we say common emitter, then we'll ground that actually node. If I say common base, we'll actually ground the base. If we say common collector, we'll ground the collector, and then we'll think about the input and output. So as the name suggests, it's a common emitter actually configuration. So we will actually ground this emitter segment. So it's directly connected to the ground. So that emitter voltage is 0, right? Do you understand? The voltage of emitter VE should be 0 because it's connected to actually ground. Now we have only two options left. Means one terminal is connected to ground, so we have two options: is the base and the collector. So in one terminal we'll connect input, and in another terminal will be actually collecting the output. So the common practice is to apply in the input. So this is our input. So this is our input signal. So this is AC signal, and we actually supply this connect this input signal to the base with some sort of actually DC resistance, let's say that RBase. And you see the another terminal of this input is connected to ground. So what does it mean? If this is ground, means this are internally connected, right? Because this is ground and this is ground. So this is the input side. Similarly, the output side, we connect a load resistance. So across this load resistance, we will be actually observing the output. So this output is equal to VC. This output is equal to VC, means the collector voltage. So again, you see for the output, another terminal is connected to ground. So internally, this is also actually connected. So what is the common point between input and output? This ground, right? So this ground means, again, this emitter point. So that's why this is called common emitter configuration. So in a nutshell, emitter is grounded, as I mentioned earlier. The input is between base and actually emitter, because this is basically emitter, right? Because this is ground, and this output is again collector and emitter, because again this point is grounded. This point is grounded. So that's why emitter is common to both input and output. That's why this configuration is called common emitter configuration, or amplifier actual configuration. So later on, we'll actually discuss like how can we control the output of such configuration by changing some, let's say the voltage, or some resistance, or the current passing through this transistor, so that we can actually desired we can obtain desired actually output in the on side. So we have other options. Let's say something called common collector. As I actually have told you about the case of when we heard the common, that means we'll actually make it grounded. So that is the easiest thing to you. So again, This is NPN transistor, and you see this arrow sign here. So this is emitter, this is base, and this is collector. There is no actual problem in identifying there's three actually terminal or nodes, right? So the common collector means we'll actually make it grounded where the collector is grounded. So this time the VC should be 0. Since we put collector as grounded, that means I have two options, two nodes remaining, which is called actually the base and emitter for input and output. So general practice, we again apply actually a input voltage through a resistor to the base. So we'll actually obtain or collect this output signal across a load resistance which is connected to the emitter, because this collector is grounded. Now, since the collector is grounded, you see the another terminal of the input is also grounded. So basically, this point is collector point, and again output terminal. One point is connected to this node, this emitter node. So basically, this is equal to VE, because E is this point, right? This node and this node are the same, and the another part of this actually thing is connected to ground. So basically, this is connected to virtually connected to the collector. So that's why common point is called collector. In this case, collector is grounded. Input is between base and collector, because this is ground, and output is between actually emitter and collector, because in some way this is connected to ground. That is the reason this configuration is called common collector amplifier actual configuration. Any question so far? Or I'm actually discussing really fast to catch. Like, do you understand what I'm saying, or should I actually go slowly, or explain it in more details, or it's fine just to follow?
Sir, I think going slowly would be better.
Going slowly should be better? Oh, okay, no problem. So there is another, these are actually conceptual part. So that's why it might be a bit difficult to understand, sometime. Later on, when we'll actually discuss about some numerical actually problem or mathematical term, it would be much easier to follow. So now maybe I can actually discuss this one in details. So there is another configuration. It's called common base configuration. So as the name suggests, common base. So what do you think? The base should be grounded, or base should be connected to input, or base should be connected to output? Just tell me. What do you think?
Base should be grounded.
Yeah, thank you so much. So first we need to know, the naming of this terminal, because this is NPN, right? There is no problem with this. And then this one is base, this one is collector, this one is emitter. As one of my students actually suggested, this base has to be grounded. So we have grounded the base. So now we have two options, like emitter and collector. So one of this actually node has to be connected to input. The another one should be used for the output. So generally emitter, the name suggests emitter should be connected to like input. As I mentioned earlier, the input is a AC signal. So this is the input is connected through a resistor, and the output is connected to the collector with the actually load resistor. So basically this V output, this node is C node, right? C point, right? So this voltage is VC. Since there is nothing in between VC and V node, so V node equal to VC. And then this is the base point. So what is the voltage of this base VB? What is this thing? 0, right? Do you understand? Because this point is connected to ground. And what is this? Like VE. And what is this node voltage? VS. So is there any confusion? And again, you see this input is connected between emitter and another side is ground. So ground means the B point, so in between base, and the output is connected between collector and ground. The ground in this case is base. So base is common to both input and output. That's why this is called common base configuration. Now is it clear?
Yes, sir.
আপনারা কি বুঝতেছেন নাকি বা আমি একা একা কথা বলছি?
না,
আপনারা
sir,
না বুঝলে আমাকে একটু ask করেন, ঠিক আছে? So I feel like this course is not that straightforward like the other courses. So best way হচ্ছে আপনারা কিছু বলবেন, মানে কোনো যদি কিছু না বোঝেন আমাকে বলবেন. I will try my best to actually explain it in the simple terms. Okay.
Sir, এখানে আমরা এমিটার কি অলওয়েজ ইনপুট হিসেবে কেন ধরতেছি? Why not the common collector terminal?
Yeah, that is a good question. Like, since we have emitter and collector, why didn't we actually put this input to collector? Yeah, we can do it, but general practice we used collector if it's available. Then we use actually collector as output, because as the name suggests, collector, and the emitter means where we actually inject the voltage or input in this configuration. Otherwise, we generally actually apply actually voltage to the base region. So basically, we'll be focusing more onto this configuration, because this is widely used for the amplification, the common emitter configuration. But these are the some configuration people should know, like what does it mean by common base configuration or common emitter or common collector actually configuration. So it might be actually a bit difficult to understand, maybe after a bit long time, but if you read it a couple of times, you will find some sort of similarities between these configurations. So this configuration now, do you think this circuit will work for this one or this one? The answer is no, because we didn't actually apply any DC biasing, means we didn't actually put any external supply to the IC or the transistor. It cannot work by itself. We need to actually apply some biasing or the voltage. So that's why this is called actually conceptual circuit diagram, because we didn't put any biasing. Means the circuit requires some sort of energy or the voltage from on the outside, right? Otherwise it should not work. So biasing is missing here. Later on we'll actually discuss about the biasing. So we discussed it already in the active mode. The transistor can be used as an amplifier. We will discuss it later. So what do we mean by biasing? So DC biasing means, in order to actually run this transistor properly in any mode, saturation mode or the active mode or whatever mode we are talking about, we must to actually use some sort of DC voltage. Generally, this voltage is around 12 volt to 15 volt. Probably you have, I think, you have taken a lab called 22206 or something like this, where you learn about this sort of transistor. If I'm not wrong, I don't know for sure. So for the DC biasing, you see, this is a normal configuration. Let's say this is N, this is P, and this is M. So this N region and NPN transistor. So basically this is NPN transistor, and this point is called collector. This is base, and this is actually emitter. So this is emitter. So now, let's say the biasing, so typical biasing circuit like this. So there is actually voltage source. VCC is generally 15 volt in some cases. In some cases, 12 volt, depending on the transistor configuration. So that is connected to the base directly through two resistance. Like there is R1, there is another R2, and then this VCC is also connected here also connected to collector region with a resistance. This is called a collector resistance, and whatever current is actually flowing through this resistance to this collector is called IC, collector current. And then whatever current is actually passing through this is called base current, which is really negligible. And there is another current passing through another resistance which is connected to the emitter. This is called RE, the resistance of the emitter. The current passing through this resistance is called IE, or emitter current. And from the O levels or A levels understanding, we know this relation, right? That IE equal to IC plus IB. Do we know this relation? The emitter current is equal to collector current plus base current. Or if you don't understand, if you apply KCL here, this IC is entering current, this IB is entering current, this IE is leaving current. So leaving current equal to summation of entering current. So this is the relation IE equal to IC plus IB. Do you know this relation, or do you recall this relation from your textbook or the previous understanding? So probably you know about this thing. So there is something called two constant for transistor. One is called alpha and one is called beta. So one is called current gain, means the factor of that corresponds to how we can actually amplify the signal. Means if we put some signal, then will it be amplified or will it be shrink, or what would be the factor of amplification? That is controlled by something called alpha and beta. Alpha is called current gain. So if I'm not wrong, that is IC divided by IE. And then there is actually something called open circuit gain, that is beta. So that is called IC divided by IB. As I mentioned earlier, that IB is very small. So IB is very small, almost close to 0 in some cases. That means some value divided by very small value. So it will be a big number. So generally in around 100 or even higher than 100. So it's a big number. So if IB is really negligible, so if this is really negligible, means let's say close to 0, not 0 exactly, close to 0. So what is the actual relation between the IE and IC? Means so whatever current is actually flowing through a collector is almost equal to the current flowing through the emitter. So IE and IC are almost equal. That's why this value is really close to 1. So in some cases 0.999 or 99 something like this. So these are the typical value, but these are just the approximation. Do you understand these relations? And there is a direct relation between alpha and beta. So if I'm not wrong, alpha equal to beta divided by beta plus 1. This is the relation. Means if you know one of this actually parameter of this transistor, let's say alpha or beta, means the current gain or open circuit actually gain, then you can calculate the other thing. So if you just rearrange this equation a little bit, so you can actually express better with respect to alpha. The relation is alpha divided by 1 minus alpha. So this is the relation. If I'm not wrong, you can check. I can make a mistake sometimes. So is it fine? This is the basic actually relation. Probably you have learned it in some courses in third year perhaps. Is it fine, the relations? Because we'll be using this relation in solving actually mathematical problem. So we already discussed about it, like the condition for the biasing for the active mode. We said it earlier. The emitter based junction should be in forward bias, and collector based junction should be in reverse bias. Now, before we talk about or drive into the mathematical actually problem or the numerical problem. So if I have this sort of actually circuit, including actually NPN transistor, how would we solve? Like what are the techniques we need to actually use in order to solve, or how can we control the output of this sort of signal? So you see, the important part is controlling this alpha or beta term, because that defines the amplification of the system, like this. If I have something here, what would be the output current, or something like this. So the easiest way, if I have a circuit like this, we need to calculate a few things. So we already have written down NPN transistor, right? This PN transistor means the base emitter in active mode. Will it be in forward bias condition or reverse bias condition? Can you recall? Can anybody tell me whether this PN junction, because this is a junction, right? This PN is a junction. Should it be in forward bias condition or reverse bias condition? Forward bias. So in forward bias, what is the voltage drop across a transistor? So if nothing is mentioned, so basically people use silicon diode. So for the silicon diode, this voltage is around 0.7 volt. It's around 0.7 volt. So basically, this is known. So the voltage between base and emitter is equal to 0.7. Even if it is not mentioned, that is the case for PNP junction. So what is VE, VBE? So VBE, we know the voltage between any two point is like this, right? VB minus VE. Sorry about the handwriting. I'm using my mouse to actually write it down. So do you understand this one? VBE means VB minus VE. So if we know VB or VE, then I can calculate the other node voltage. Why these node voltages are important? Like that VB, VC, and VE. These are the three terminals, right? Three nodes we have. The collector nodes, then base node, and the emitter nodes. So if we get to know about the voltage at this actually particular nodes, we can easily calculate what is the current passing through the system, or we can control the current by changing the resistor value. We'll discuss it later. So our target is to calculate this node voltage as fast. So you see here that this voltage is VCC, is the supply voltage, and there is R1, there is R2. So these are in series, right? This R1 and R2 are in series. So can you calculate the voltage at this point using actually voltage division rules? So what would be the VB? So can it be written like this? VB is the voltage across VB. When we say some node voltage, it is always with respect to the ground. So VB means the voltage between this point and ground. So voltage across R2. So what is the total current? VC divided by R1 plus R2. So VCC divided by R1 plus R2. That is the current flowing through this line. And this current times what? The resistance here. So this is nothing but the R2. Is it clear? Or I should actually explain it in another way. So do you understand? If I have this sort of actual circuit, we can calculate the base voltage directly using voltage division rule.
Yes, sir.
Thank you. So if I know VB, and if I know this relation that VBE equal to 0.7, so VB minus VE equal to 0.7, can we calculate VE from here? We know the VB, right? So can we calculate VE from here? Because if I know the VB value and put it here, can we calculate VE value?
Yes, sir. VB
Yes.
minus 0.7.
Yes, yes. Thank you so much. So if we know VE value and another terminal is ground, and if this resistance is known, can we calculate IE? What is the relation of IE? IE is the current passing through this resistance, right? This resistance is connected between E means VE and ground, right? Can we write down VE minus 0 divided by RE? Can I write down like this? কোনো প্রবলেম আছে এটা লিখতে, এই কোশ্চেনটা লিখতে? No. So we have calculated VE from here. So if we plug in this value here, then we can actually control the current through the emitter. If we change the same resistance in the emitter, then this current will be actually changing as well. Once we get to know this IE, the another thing should be given either alpha value or beta value. So if I know alpha or beta value, I can easily calculate IC value using these formulas. So if I know IC value, then what is the relation of IC in terms of actually KVL equation? The IC is current actually passing through this RC resistance. The RC resistance is connected between VCC and that VC collector actually voltage, which is the output voltage. This is VC divided by RC. If RC is known and IC is known, can we calculate VC? You can easily calculate VC, right? So this is the conceptual way of solving this sort of actually circuit. Later on we will be solving a real mathematical actually problem. So আপনাদের কোনো কোশ্চেন আছে? একটু মেসি মনে হচ্ছে, বাট যখন একটা ম্যাথ অথবা কোনো কিছু সলভ করব, hopefully it will be clear. So
IC.
Definitely. So this RC, this IC is the current passing through the current passing to the collector, right? So that this is the collector point. You see this resistance is connected between VCC, means the supply voltage, and collector voltage. So what is the current passing through this voltage minus this voltage divided by this resistance is called current, right? The Kirchhoff law or the Ohm's law, the voltage divided by resistance equal to current. This is what we have used here. Now is it fine? How do we know this IC value? You remember, if we can calculate IE, means the emitter current, and if alpha or beta, any one of this actually are known, then we can calculate easily what would be the IC value for this actually transistor. Then we can easily calculate what is the actually collector voltage or the VC voltage. So basically what our chairman sir has done, he has actually written down all the equations here, whatever we have discussed here. Probably I am using different actual method to solve, but he has written down the same equations, if I'm not wrong. Those are the equations we discussed it already. So this is the designing actually thing. So let's say this is the equation I just have written. You see this equation. This equation. So if I rewrite this equation, VCC should be equal IC times RC plus VC, right? So he has written the same equation here. If I'm not, he has written the same equations here. So these are the like designing issue. Let's say if we know this equation, so designing should be very easy. Means what is called designing? Let's say I wanna fix it at certain value, 5 volt, and I wanna have certain amount of actually current passing through the emitter. What would be the resistor value for this actually system? So we can easily calculate using this formula. So that is actually the designing part. The rest probably you don't need to check. You'll just read this thing. Those are the only conceptual things. But there is something is important for a transistor, which is called Q point. Quiescent point or Q point is nothing but the collector current and collector voltage. You remember we had written down some equations here. So if we can calculate the collector current, and if we can calculate the collector voltage, that coordinate IC comma actually VC is called actually Q point. So now maybe I can save it for now, and we can go back to some mathematical actually problem. So this problem has been taken from the reference book, Cedar Smith. So maybe actually we can actually discuss it in detail so that we will understand it in proper way. So this is a really basic actually problem. Actually using some color pen. Should I use red color? Is it easy to follow? So the question says, the transistor in this circuit has a beta value. As I mentioned, something should be given, either alpha or beta value is given. And also said, VBE, the base emitter voltage is 0.7 volt. Where do we actually get, this 0.7 volt? Remember, this is in this. This is the emitter, this is base, and this is collector. Is there any actually problem in identifying this actually node collector base emitter? Probably not. And this base emitter should be in forward bias, right? So base emitter is a PN junction. So if it is in forward bias, what would be the voltage between the base emitter is 0.7. That's why that is actually given in 0.7. It's also actually given that collector current is 1 milliampere. So design the circuit. So we need to design the circuit. So there should be something unknown. We need to find that value. And it's also actually given this 1 milliampere. So it says, design the circuit in a way 2 milliampere current flows through the collector. So that means this collector current is equal to 2 milliampere. And it also says voltage plus 5 volt is appear in the collector. That means collector voltage is also given to 5 volt. Do you understand the question? Then we'll understand, we'll actually see, how to solve the question. So if this one is the case, from the circuit, what is the base actually voltage? The base is connected to ground. Okay, yeah, question.
এখানে তো জাস্ট ডিসি ভোল্টেজ আছে, কোনো এসি ভোল্টেজ নাই, কিন্তু এখানে আইসি মানে এটা দিয়ে কি এসি বোঝাচ্ছে? মানে প্রথম আইসি ইকুয়াল টু 1 মিলি অ্যাম্পিয়ার।
No.
Continuous.
It was a good question. So basically, this voltage was given like when this like PN junction or the transistor was tested at this particular current is passing through this like transistor. They have calculated a VB equal to 0.7 volt. But when 2 milliampere current is flowing through this one, basically this barrier voltage is no longer 0.7 volt, but it has a different formula, like I think VBE plus ln something, this current by this current, but we are not using this actually thing. So we'll consider this barrier voltage or the on voltage should be remain constant, means the 0.7 volt. So no, that is not an AC current. Okay, so that is for the testing of this what is it called, the transistor. So we'll consider VB equal to as constant. Maybe I can actually show you the workout from here. That is 6.2, right? Let me see, 6.2. This is is this 6.2? You see, they have calculated VBE using this formula. So 0.7, because that is the ideal value, plus VT, thermal voltage, then ln of the new current divided by the testing current. So new current was 2 milliampere and testing current was 1 milliampere, but the result should be almost close to this one. So basically we are not using this one. We will consider this barrier voltage would be constant, means 0.7 volt. It would be easy. It will be easy to solve the question then. So that's why it was given. It was for the testing of this actually transistor. So how to solve this one? Remember, we will try to actually find out the three node voltage, the key node voltage, the base voltage, emitter voltage, and collector voltage. So what is this base voltage? Base is connected to ground. So what is BB? Can you tell me? আপনারা রানিং স্টুডেন্ট, আমাদের থেকে ভালো পারার কথা আপনাদের, হ্যাঁ? I guess it is 0. So we know another thing, right? That VBE equal to how much?
0.7.
Thank you so much. So what is VBE actually? VB minus VE because VV means the voltage between actually base and emitter, right? So V minus VE equal to 0.7. Is it clear now?
Yes, sir.
Thank you. So what is VB value? 0, right?
Yes, sir.
So what is VE?
Minus 0.7.
Thank you. So that is minus 0.7. So if I know this is minus 0.7, and you see this voltage is negative 15 volt, this voltage you know now, what is the current passing through this? This current is called IE, right? So IE, as I mentioned earlier, IE is the current passing through, that's RB resistor, So what would be this value? Let's say we can write down VE.
Minus 0.7 plus 15 divided by RE.
Exactly. So I didn't put the value of V here divided by RV. You understand this one? I just applied the Ohm's law here. This resistance is connected between the E point and this point, so the voltage difference between this point is VE minus, and this value is negative 15. So I put in the negative 15 here, divided by RE, voltage divided by resistance, should be equal to actually current, right? But what was given here, the question was really straightforward. IC value equal to 2 milliampere, right? And this is beta. So what is beta formula? Beta equal to what? Beta equal to IC divided by IB, right? So IC is known, beta is known. Can you calculate IB? You'll see, this value is very small. So if you know IB, then IC, can you calculate IE? What is the formula for IE? IE equal to IC, excuse me for my handwriting, IC plus IB. Do you understand this part? So can we calculate, so IC is given. If I put this value, beta is given as well. So can you calculate IB? Can you calculate IB? Which should be straightforward, 2 divided by 100. So that is the IB value. This should be 2 divided by 100. So similarly, for this one, so if I know IB and IC, if I put it here, can I calculate IE? একজন বলেন যে ক্যালকুলেট করা যায় নাকি আমাকে এক্সপ্লিসিটলি ক্যালকুলেট করতে হবে?
স্যার আমার কাছে তো আইবি আছে আর আইসি তো স্যার আমি বের করলাম, সো করো তো
easily করা যাবে, ঠিক আছে, no problem at all. So আমি যদি if we calculate that IE value and plug in this IE value here, we know that V, which is negative 0.7, we know IE. What was unknown? RE, right? Can you calculate RE from here? Yes, right? Everything is known. This one is known, this one is known, this one is known. We can calculate it easily, RV. So that is one design problem, because that was unknown, we have calculated. Now there is another unknown, which is called RC. We need to calculate RC value. So RC is connected between this point and this point. You see the collector voltage was given 5 volt. So give me a second, what happened to my mouse? So this RC is connected between this voltage and this voltage, and the current passing through this is called IC. So what is the relation? IC equal to this 15 volt minus what? This VC divided by RC. Is it clear? নাকি খুব কঠিন মনে হচ্ছে এখন? কঠিন মনে হচ্ছে নাকি?
হয়ে গেছে স্যার,
বুঝছেন আরেকবার বলেন।
স্যার একটু মেসি হয়ে গেছে তো স্যার, বুঝতে একটু সমস্যা।
হ্যাঁ এক্স্যাক্টলি, কারণ আমি মাউস ইউজ করছি আর হোয়াইট বোর্ডে হইলে হয়তো বা বেটার হইতো। সো এগুলোর ওয়ার্কআউট হচ্ছে আপনার বইয়ে করা আছে। আমি এই এক্সট্রা যে জিনিসগুলো অথবা ম্যাথমেটিক্যাল প্রবলেমগুলো পড়াচ্ছি এগুলো আমি আপলোড করে দেবো, ঠিক আছে? তারপরে আপনাদের দেখার পরে যদি কারো প্রবলেম হয়, আমার কনসালটেশন আওয়ারে হোক অথবা ক্লাসের পরে হোক অথবা ক্লাসে হোক, আমার সাথে ডিসকাস করবেন। ইনশাআল্লাহ I will try my best to clear the confusion. So as I mentioned, this IC is the current passing through this resistance. Whatever question you have, you can ask.
Sir, I have another class now.
Sure.
Okay. Sir, should I put my ID here for the attendance?
This is the question. Yeah, you can actually leave your ID here for your attendance. No problem. So this IC is the current actually passing through, this resistance, this the RC. So if I apply, the the KVL, the current should be, the voltage difference divided by, the resistance. The voltage difference is 15 minus, VC divided by, the resistance is RC. So now, that VC value, this VC value. Maybe I can put in this one. Yeah. What is the IC value? 2 milliampere. So 2 milliampere. And that equal to 15 minus VC. It was given 5 volt minus 5 volt. And divided by RC value. We need to calculate RC value. So you see everything is known other than in RC, so you can calculate in RC from here. So this is the design problem. For this actually particular configuration or this specification, we need to calculate this unknown resistance. The RC means the collector resistance, and that emitter resistance that we have calculated here. So this is the case. The similar problem is given here. This one should be in the homework. You can actually give it right. So if you face any problem, you can talk to me later. That should be the the homework. So maybe these are a bit actually complicated. The other questions, so we'll discuss it in the next class. So before we actually end for today's class, আপনাদের কাছে একটা কোশ্চেন ছিল, সেটা হচ্ছে যে আগামী আপনাদের সাথে ক্লাস আছে কবে? আমার বুধবারে রাইট?
Yes, sir.
তো বুধবারের ক্লাসটা আমি অনলাইনে নেব, বুঝেছেন? আমি একটু অসুস্থ, সো আমি দেশের বাড়িতে আছি। নেক্সট উইকে ইনশাআল্লাহ আমি ইন পারসন ক্যাম্পাসে থাকবো। সো কারো কোনো প্রবলেম আছে যদি আমি অনলাইন?
টাইমিংটা কখন হবে?
আপনারা বলেন কোন টাইমটা আপনাদের জন্য
রাতে করে দিলে ভালো হয়।